Okay, so we're finishing up chapter 4. This is the last part, chapter 4.6, which is called Solution Stoichiometry and Chemical Analysis. So you're going to want to need your, you're going to want to take out your notes, and you're also going to need Solution Stoichiometry 4.6, because we're going to work on that right after. So, oh, and you're going to also need, this is what the notes on titration look like, and this is where you don't have these notes. I'm going to be reading over this in this session. So I have included an attachment in Edmodo for you to print this out. It's 2 pages of titration notes. Okay, so that's everything you're going to need. Remember, the test is Wednesday. All right, so let's get started. Imagine you have to determine concentration of several ions in a sample of lake water. Number 1, chemical reactions like we have discussed continue to be used to figure this out. For example, what I mean by that is we've discussed double replacement reaction, or aka precipitation reaction, aka metathesis reaction. We also discussed single replacement reaction, which is also called redox reaction, and we've discussed neutralization reactions. So when you read this sentence, it's keeping in mind all the different types of reactions that we have discussed in this chapter, and these types of chemical reactions continue to be used to this day. They are carried out in a real situation where you have to determine the concentration of several ions in a sample of lake water. Recall that we learned if you know the chemical equation and the amount of one reactant consumed in a reaction, you can calculate the quantities of other reactants and products. So we're going to actually do a problem down here where this point number 2 makes a lot of sense. Number 3, recall that coefficients in a balanced equation give the relative number of moles of reactants and products. So in this part of the chapter, you're actually going to have to put everything you learned together. You're going to have to balance equations. You're going to have to use the molarity formula. And you're going to also have to remember stoichiometry that we learned from even last year. And we also practiced in the beginning of the year. So it's a combination of everything, and it all culminates and comes together here in this section. And that's why you're going to see that the sample exercise is definitely a higher level of difficulty, because you're taking all of your skills now and applying it to one problem. When dealing with grams of substances, we use molar mass to make the conversion. And you know that based off of basic stoichiometry principles. And when working with solutions of known molarity, we use molarity times volume to determine the number of moles. So let's work on a problem, and then I think that what I just wrote here is going to make a lot of sense to you. So you have to open up to page 152, and we're going to do sample exercise 4.15. And as we do this, let's take it a little slow, because you are definitely going to be using a lot of critical thinking skills as you move through solving this problem. So it asks how many grams. We're looking for, the unknown is grams. Oops. How many grams of calcium hydroxide is needed to neutralize. Now, you see that word neutralize right away. You're dealing with a neutralization reaction. Okay, there's something from earlier in the chapter, so you're going to have to freshen up your knowledge on what exactly is produced when you have a neutralization reaction. And then you have 25 milliliters of a 0.100 HNO3. All right, so let's talk about strategy. Like, how would you attack a problem like this? We need to figure out how many grams of calcium hydroxide are needed to neutralize 25 milliliters of a 0.1 HNO3. So let's put down the reactants. The reactants are, and we're going to try to get a balanced equation here. And we have calcium hydroxide. And based off of our neutralization knowledge, we know from these notes here that a neutralization reaction is actually, I told you to put at the top, it's actually called acid-base neutralization reaction. It's when a solution of an acid and a base are mixed together. Here's the important point that you need to know to do this problem. It's prior knowledge that this produces water and a salt. Or you could also look at it, because they both have partners, they switch partners, and we know from that it's like a double replacement reaction. This is AQ. Okay, so products are H2O liquid plus the salt, which is, I'm writing the wrong one, CaNO3 aqueous. And remember, in this case, I was thinking salt NaCl. In neutralization reactions, salts are any ionic compound whose cation comes from a base, example, sodium from sodium hydroxide, and whose anion comes from an acid. An example is hydrochloric acid. Okay, so in this situation, this is a salt because the cation comes from the base. Okay, so here's your cation that comes from the base, calcium hydroxide, and whose anion comes from an acid. And the anion is the nitrate polyatomic ion. So this is, with that definition, that would be considered a salt. So you have a water and a salt in a neutralization reaction. Now, this thing is not balanced. And you would definitely, if you had to work this out, you would have to take the time to balance it, but for sake of time, I'm going to just do it. This is a balanced chemical equation now. All right, so now we have it balanced, and so what are we going to look at next? We know, based off of the definition of molarity, let's write that out. Molarity, capital N, equals moles of solute. Let's keep writing this out so that we drill it into our mind. Moles of solute over volume in liters. It's the volume of solution in liters. And we have, and remember the other thing that I told you, that if you have any, there's 3 factors here, and if you have any 2 of the 3 factors, then you can solve for the unknown. So as you can see, we have 25 mils, which is volume. So let's just plug it into the equation. We have 25 mils, and we actually need to change that to liters. So and we have molarity 0.100, and we want to solve for moles of solute. So when we do the math, we end up getting the moles of HNO3 is 2.50 times 10 to the negative 3 moles HNO3. Okay, now we have to remember basic stoichiometry, and this is why you have a picture of this diagram on the worksheet. The reason why is it comes into play with this problem. So if you are trying to, in a neutralization reaction, you would definitely have to refer to this, because if you have moles of HNO3 and you want to convert to moles of calcium hydroxide, you would need to go do a mole to mole conversion, and then once you get the moles of calcium hydroxide, then you do a mole to grams conversion. So to do this, you start with 2.50 times 10 to the negative third moles of HNO3, and to change that to moles of a mole to mole conversion, it says here, use the coefficients from the balanced chemical equation. So to get rid of moles of HNO3, we see that there's 2. The coefficient here is 2, so we're going to do 2 moles of HNO3, and we're going to put that over, we're converting now to moles of calcium hydroxide, and we can see the coefficient is 1. Opposite sides cancel, and now you successfully convert it to moles, but the problem's not asking you to give the information in moles, or the answer in moles. It's asking you to convert it to grams. So in order to get it to grams, you're going to do 1 mole of CaOH, and then you're going to, opposite sides cancel, and then you're going to put that over the formula weight of calcium hydroxide, which is 74.1 grams of calcium hydroxide. And when you do all of that, you come up with an answer of 0.0926 grams of calcium hydroxide. Now, as I wrote a little note here, this was definitely, this problem is a higher level of difficulty, because what you need to take into consideration is you needed to balance the equation. You also needed to understand what a neutralization reaction was. If you didn't look that up, then you would not have known that the product is a water and a salt. You also needed, I said this, right, the molarity formula. And then you also needed your stoichiometry diagram to navigate from moles, a mole to mole conversion, and then once you got to the mole of calcium hydroxide, then it helped you to figure out how you were going to get to grams of calcium hydroxide. So as you can see, everything has culminated by the end of the chapter, and you have to take your knowledge from a whole bunch of different sources, put it all together to solve a problem like this. And I would definitely recommend doing the practice exercise on page 152 on your own. Sample exercise 415, do the practice exercise underneath of that. Okay, so let's turn the page, which is actually this. Now we're going to talk about titrations. Titrations, this lab procedure is used to determine the concentration of a particular solute in a solution. So here is why we do titrations, because we're trying to find the concentration of a particular solute in a solution. The technique requires a sample of the solution to mix with a reagent solution of known concentration. This is called a standard solution. So the procedure requires, in order to find the concentration of a particular solute, which you don't know what that concentration is, it requires you to mix with a reagent solution of known concentration, and that is called a standard solution. Not to be confused with what we learned about in dilution, which is stock solutions. Stock solutions are solutions that are routinely in the lab, and they're prepared in concentrated form, like hydrochloric acid is always purchased at 12 molarity solution. This is a standard solution, and this standard solution is used in a titration method so that we can, it has a known concentration, and then it'll help us to determine the concentration of an unknown solute. Titrations are conducted using acid-base reactions, precipitation reactions, and redox reactions. Okay, so you would use titration for all three of these. Remember, precipitation reactions, let's start with acid-base reactions. They're called redox reactions. You would use the activity series. on the test. This is single replacement reaction. And it's no reaction if the, let me see if I can find it real quick. It'd be considered no reaction if the metal was lower. For example, if you were dealing with gold, can gold displace zinc? And you would say no reaction because gold is lower in the activity series than zinc. Okay, I'm just trying to refresh your memory to some of this because you're going to be tested on all of it. Now, a precipitation reaction is a double replacement reaction, and here we're looking for the product to be a solid. And what do we use? We use our solubility rules chart. I'm going to write a note here too about solubility rules chart and your activity series, because I want to find out if you're going to be provided with these charts for the test. So that's just a note for me to check on that. Okay, so precipitation reactions, we're looking for a solid. Remember, these reactions have like a double partners, like NaCl plus CaOH. And they're the reactants, and essentially they are going to switch partners. So they're, this would be aqueous. And actually, OH is usually always, let me see, I'll make that, this would have to be LiOH, because then it's aqueous. All the alkali metals in group 1 are all aqueous. So when you do I'm doing this right off the top of my head, so this would have to be calcium chloride, aqueous. Okay, so when you do the, reaction, they essentially switch partners. So it would be outer and then inner. So it's Ca calcium hydroxide plus lithium chloride. I'm doing this off the top of my head. I know hydroxides are solids. So this one, the reaction would happen because I know that hydroxides are always insoluble. How do I know that? Because of the solubility rules chart. Redox reactions are, this is a neutralization reaction. And this you would use an activity series. Redox is oxidation reduction reaction. I'm sorry. So this is what you would use the activity series for. Acid-base reactions are neutralization reactions. They form a water and a salt. Okay. C. If we have unknown hydrochloric acid solution, we take the sodium hydroxide reagent, which is the standard solution of a known 0.1 molarity. We measure specific volume of hydrochloric acid. The specific volume is 20 mils. Then we slowly add sodium hydroxide until the neutralization reaction is complete. The point at which stoichiometrically equivalent quantities are brought together is called the equivalence point of the titration. That's a vocabulary word. Equivalence point of the titration. In order to titrate an unknown with a standard solution, we need a way to figure out when we have reached the equivalence point of titration. So now you're going to look at figure 4.20 on page 153. Okay, here, so in figure 4.20, we can see that on A, we have hydrochloric acid and it's colorless. And we are trying to figure out, by using this burette, the unknown concentration of hydrochloric acid, and we're going to figure out when the equivalence point has been reached based off of an indicator that we add in the hydrochloric acid. So we're going to put in what's called phenolphthalein. Phenolphthalein is an indicator that in the presence of an acid, it is clear and colorless. But as you start to add the standard solution, which is sodium hydroxide, little by little you let drops go in. The end point will approach and you will start to see a pale pink color form when the base is added, because phenolphthalein is an indicator that in the presence of a base it turns pink. Once you begin to see the pale pink color form, this notifies us that the end point has been reached, and the pink becomes even more brilliant as you add more base to the solution. So let's go back to this. In acid-base titrations, dyes known as acid-base indicators are used for this purpose. And the purpose is we need a way to figure out when we have reached an equivalence point. And that's where the indicators come in. One indicator's name is called phenolphthalein. Phenolphthalein is one type of indicator, there's many of them, that it's colorless in an acid but turns pink in a basic solution. If you add phenolphthalein to acid, the solution will have no color. Then when you slowly add the standard solution, the base, from a burette, you continue to add it slowly until the solution barely turns pink. Once you see that very light pink color, it means the color change means that the acid has been neutralized, and the color change indicates that the end point that you have reached the end point of the titration. This coincides with the equivalence point. So you could say end point or equivalence point. Those two words coincide with each other. And remember, when you look here, that an equivalence point is the point at which stoichiometrically equivalent quantities are brought together. Okay, and the way that we figure out when we have reached the equivalence point is by adding an indicator. And in this example, they added phenolphthalein, and when the base, which is sodium hydroxide, was added to the acid, we know that we have reached the equivalence point when the solution turns pink. I hope you understand the concept of titration, because you will be definitely doing these in the lab. Okay, so that's basically the only time that you are using the coefficients in the balanced equation is when you're doing a mole to mole conversion. It's never when you're doing a gram to mole conversion. It's always 1 mole over a gram to mole conversion. But when you're doing a mole to mole conversion, make sure you look at the balanced, the coefficients in the balanced chemical equation. Okay, opposite sides cancel. And then we are going to look for grams of iron. So we're going to put 1 mole. Notice I only used 1 mole. That's because I'm doing a mole to gram conversion. So I'm going to put 1 mole here and not 3, because 3 only comes in when you're doing the mole to mole conversion. Very, very important. Okay, so 55.85 is the weight of iron, if you look that up, the formula weight. And opposite sides cancel. Now we successfully convert it to grams of iron, and if you do the math, it's 336 grams of iron. Okay, that is a review of the stoichiometry. Now, this one is how many grams of calcium hydroxide are needed to neutralize 25 mils of 0.1 molarity HNO3. We did this already. Just copy it from our notes, because you're going to have to hand this in for credit. So just copy it straight from the notes. We already went over it. And you're going to do this one by yourself. Almost done. And now we're going to do titrations. Chemists perform titrations to determine the concentration of a particular solute. It's an unknown solute in a sample. This is completed by taking an accurately known amount of sample using a pipette and slowly adding a stock standard solution. Chemists know the concentration of a standard solution very accurately. Therefore, when the reaction reaches completion, stoichiometry can be used to calculate the concentration of the unknown solute. When reactions reach completion, this is called the equivalence point. In acid-base titrations, an acid-base indicator, and we learned was in that last example was phenolphthalein, is used to determine the equivalence point. Now, okay, so let's look at this picture here. We have the procedure for titrating an acid against a standard solution of sodium hydroxide, and there's a known quantity of acid that's added to the flask. So we take the pipette and we take 20 mils, which is the known quantity of the acid, and we put it in the flask. And then B, an acid-base indicator is added. Here's your, and you get the initial volume reading of the standard solution of sodium hydroxide in a burette. And sodium hydroxide is added until the neutralization solution occurs, where the indicator now has changed color, and then you get the final volume reading. Okay, so this is basically the procedure for titrating an acid against a standardized solution of sodium hydroxide. Okay, so we're going to do the sample exercise. One commercial method used to peel potatoes is to soak them in sodium hydroxide solution for a short time. Then remove them and spray off the peel. The sodium hydroxide concentration is normally 3 to 6 molarity, and the solution must be analyzed periodically. In one such analysis, 45.7 mils of 0.5 molarity sulfuric acid is required to neutralize 20 mils of sodium hydroxide solution. What is the concentration of the sodium hydroxide solution? Okay, so the first thing, we're given the volume, which is 45.7 mils, and we're given molarity of sulfuric acid solution that reacts completely with 20 mils of sodium hydroxide. And we're asked to calculate the molarity of the sodium hydroxide solution. So our plan is that we're going to use the volume and molarity of the sulfuric acid to calculate the number of moles of the substance. So we write out the equation: molarity equals the moles of solute over the volume of solution in liters. And to solve for moles, you're going to take 0.457 liters of solution, and you're going to put 0.5 molarity, and you're going to solve for X. And when you do that, you get let's see, figure that out. Okay, it's 2.28 times 10 to the negative 2 moles of sulfuric acid. Acids react with metal hydroxides to form water and a salt. Thus, the balanced equation, you need a balanced equation here, for the neutralization reaction is okay, so this is our balanced chemical equation, and now we're going to do solve for moles of sodium hydroxide, and we get the 2.28 times 10 to the negative 2 moles of sulfuric acid, and we know that there's a ratio of 1 to 2. Opposite sides cancel, and we're getting 2 moles of NaOH. And when you do the math, you get 4.56 times 10 to the negative 2 moles of NaOH. Okay, knowing the number of moles of NaOH and 20 mils of solution allows us to calculate the molarity of this solution. So molarity, NaOH, equals moles of NaOH over the liters in solution. And when you plug that in, you get 4.56 times 10 to the negative 2 moles of NaOH over 20 mils of solution. And you have to turn that to 1,000 mils of solution over 1 liter of solution. And you get 2.28 moles NaOH per liter of solution. So that equals 2.28 molarity. That's your final answer. Okay, so now you have to do the practice exercise. Okay, so this is the test review. We're going to go over really quick what you should study for the test. Chapter 4 test review. The first thing that you need to make sure you understand is what is a soluble ionic compound. What is a soluble molecular compound? The species present, what species are present in a weak acid? Strong base and a molecular compound. You need to understand what diprotic versus monoprotic acid. You need to know the difference. You need to know oxidation numbers. You need to know how to calculate molar concentration of a solution. Which is the capital M molarity, which equals moles of solute over volume in liters. You have to, there's going to be a few questions like that. You have to know how to read the activity series. You have to understand what is oxidation and reduction. Oxidation, reduction, what is happening in these reactions. Remember Leo, the lion says Gur. So Leo is loss of electrons is oxidation, and Gur, gain of electrons, is you you have to understand a dilute solution. A dilute solution, the solute is sparing, more sparing than in a concentrated solution, which the solute, there's more solute in a concentrated solution versus a dilute solution. You need to, this is dilute, concentrated solution. You have to be able to balance an equation. Balance an equation and write the net ionic equation. That says net ionic equation. And you need to locate spectator ions. And an example of that is a double replacement reaction. And when you have a double replacement reaction, you are dealing with the solubility rules. And if there is a solid in the product, then the reaction has taken place. And when you find the spectator ions are the ions that are not players in the reaction, in making the solid. So if you have calcium hydroxide solid and you have NaCl, I'm just making one up off the top of my head. That would be all right, so in this situation, what are the spectator ions? The spectator ions are the ions that are not involved in forming the solid. So cross out Cl and Na. So as you can see, it's Ca plus OH makes calcium hydroxide solid. This is a 2+, and this is a 1-, and just make sure this is balanced because I made this up off the top of my head. And if it asks for spectator ions, the spectator ions are sodium and ion and the chloride ion. All right, so that's how you do that. And what is the volume? You're going to have to know volume. You're going to have to understand neutralization reactions.
Oh, stinks die.
Basically, the reaction that we did, I'm looking for it. The one that's on the sample exercise 4.15 on page 152. Understand that. Go over it, look it over. And that was on page 20 of your notes. Make sure you look that over. So that's a neutralization reaction. And you're going to want to write out the equation first. Balanced chemical equation first. And you're going to also have to use your stoichiometry skills. And the other thing that you need to know is the difference between non-electrolyte, weak electrolyte, and strong electrolyte. Okay, so I helped you by giving you the 12 main points on the test, so make sure that you know this inside out and upside down, and you will do just fine. I know you will. I trust you that you guys are going to do a great job and make me proud. Okay, so next time you hear from me, we're going to be moving on to Chapter 10. All right, I hope you do well on the test, and make sure you send me your scores. Let me know how you did after they get graded.